Hi, everybody. This is already your week 8 welcome video. We are so close to the end here, and I'm so impressed with everything you guys have been doing. So first of all, this is the last video exactly like this, okay? Because week 8 is the last week of the course that follows the same pattern we've been following. So we are there. This is the last release of a week's worth of material. So that is very exciting. You'll see what's in the material when you look at it. But one heads up is that we're doing a prediction contest this week. It does not matter whether you win the contest. Your grade on the assignment has nothing to do with whether you win the prediction contest. But what we're going to do is work on the same model that you were thinking about on the last assignment, which is predicting the FT feminist variable using other things in the data set. And you are going to each try to come up with a model that is the best model you can come up with for making predictions for FT feminists. And again, you'll learn a lot more about how to do that when you watch the videos for this week, but that's what you're going to be doing. One thing that is highlighted in the videos and also highlighted in the assignment, but that I've learned I have to highlight out loud right now as well. The idea is that you are going to split the data into 2 parts, okay? And I've given you exactly the code that you need to do that so that everybody splits it into the same 2 parts. And you're going to fit the data to 1/2. Sorry, be careful. You're going to fit the model to 1/2 of the data and then use that same model, so the same coefficients that you estimate, to make predictions for the other half of the data. Okay, that's called cross-validation. Again, you'll hear me talk more about that idea. But the reason I'm mentioning it now is that there's a common error, which is to take the half of the data you're fitting the model to, figure out which predictors you want, right? So maybe it's going to be FT feminists being predicted by outraged, right? Maybe that's your final model. What you're supposed to do is say, okay, so my model is that the mean of FT feminists is, I don't know, 40 plus 3 times outraged. And then you're supposed to take that equation to the other half of the data set and say, okay, 40 plus 3 times outraged, what are the predictions, right? That's what you're supposed to do. A common error is to say, okay, my model that I've chosen has outraged as a predictor, and then go to the second half of the data and run the LM command again and re-estimate the coefficients and get something like 37 plus 4 times outraged, which is a different model, right? That is not what you're supposed to do. If you find yourself running the model again on the second half of the data, then you've made this error. I guarantee some people make it anyway and will help you, but I just want to mention that there's something to look out for that is a common conceptual error when you get to that. Okay, so but as you go forward, there'll be lots more reminders about that idea. I also want to give you a preview of how the course is going to finish up. I'll talk more about this next week from today, right, as well. But this is the last regular week, so everything will be due on, for everything for week 8 will be due on Wednesday, July 27th. The day before that will be the last lab. Okay, so labs finish with week 8. There are no labs on July 28th or July 29th. Okay, no labs. You do not have to go to lab in those days. Your labs will have finished. So this is the week to say goodbye to your TAs, right? And your new lab buddies, right? This is the last week of regular labs. However, on that Thursday and Friday, July 28th and July 29th, we will run some office hours at times that are TBA. Okay, so those will have some time because you'll have one more thing due for those last couple of days. And that's going to be a final quiz. Okay, the final quiz will be, I think, probably 30 questions. It'll be a little bit longer than the quizzes you've been seeing. And it will be different because it's not just questions that you're supposed to discuss with everybody, but rather a set of questions that you're expected to sit down and do in an exam type format, right? So you're going to not talk to anybody. You're not going to use any resources. You're going to do it in one sitting, right? So you're going to spend like Wednesday, Thursday, Friday, next week, the 27th, 8th, 9th, studying for a quiz. And at some point, you're going to sit down and actually take it and answer the questions and submit it. The quiz will mostly draw on the previous quizzes. Okay, so it's a lot of it is a random sample of questions from the previous quizzes, but they won't be multiple choice anymore. Or maybe I'll change the numbers a little bit, right? Something to check your understanding so it's not just memorization. And then there'll be other questions that are not just drawn from the quizzes, but it'll still be a Google form and it'll still be, type somewhere, type a brief sentence or, type in a number. It will not be, long calculations or R coding or anything like that. So that just so you know what's coming, right? So when I post the conclusion video, what you'll see there is that I'm announcing this quiz. I will be announcing the office hours. I'll be announcing the results of the prediction contest. And I'll be telling you that we're posting an SEQ, right? So those are the things that are coming next week. Just so you can plan your time as we end up the summer, which is very exciting. there are two more things that I want to do right now. One is to rant a little bit about one of the graphics we saw this week. And the other one is to show you a little bit of code, some of the ideas that I ended up talking to several students with this week that I thought would be useful for everybody. So this is the graphic from Monday, the graphic of the day from Monday. Okay, so here it is. Okay. So for those of you, most of you did look at this graphic because most people have lab on Monday. I'm zooming in a little bit. So this is the margin of victory for Obama versus Romney in each county in the US. You can't see it for all of them. So what they've done here is they've used a map. So lots of you are learning about using maps, which is fantastic. Maps are useful when you can assume that your audience knows something about the locations of the units in your data set, right? Because then it's easy for us to find ones that are familiar to us. And what they've chosen to do in this graphic is they've represented the number they're trying to show, so the margin of victory, by the height. So they've essentially made a little prism in the shape of each county, right? So this county over here must be in this shape, and they've made it kind of stand up like a little plateau, right? And here, this King County is in this shape, they've made it stand up, okay? So what I want to point out here is that I think, although this is pretty, okay, although maybe it looked nice in a magazine, this graphic is one of the worst violations I've seen of this principle that every element of a graphic should be proportional to the number it represents. Let me zoom in again because I can't see the numbers otherwise. So for example, I see in Brooklyn, New York, so that's part of New York City, the margin of victory for Obama was 191, 100,000, right? 191,000, right? So it corresponds to this bar, which you can not really even see, right? Because Brooklyn is a very small geographical area, although it has a lot of people, right? That's just a skinny little peak, okay? And we can compare that to Broward County in Florida, right? Also has a margin of victory for Obama, 191,000, but it looks totally different, right? It's hidden behind this other one. It's wider. It is the same height, but you can't tell at all, right? There's no way that you can look at this picture and see that those two things are the same number, right? Similarly, looks to me in this map that the height of this looks like a tower to me for Brooklyn is about the same height as the one for Philadelphia, right? But because the area of Philadelphia is a little bit bigger than the area of Brooklyn, this tower here actually represents 460,000, and this one represents 191,000. And this one's also 191,000. Look at that, Middlesex County in the Boston area. But it's much shorter because Middlesex County covers a broader geographic area. So again, although this looks pretty, right? Oops, although this looks pretty, this picture totally violates the principles that we've been discussing. And so again, if you were trying to make a pretty illustration to capture people's attention, sure. But if you are trying to claim that you are somebody who knows how to deal with data, you should not make a picture like that. If you wanted to graph that data in a different way, one option would be to use a color scale to show the margin of victory. It wouldn't be as flashy, but you'd actually be able to compare the color of Brooklyn maybe to the color of someplace else. Or if you want to deal with the fact that, for example, Brooklyn's very small, it might be hard to see, you don't have to make a map, right? You could say, here are the margins of victories in the counties that had the most extreme margins in either direction, and make a bar plot, right? Is it as flashy? No. Is it much better? Yes, right? It's much better because you are in the picture we're showing, you're making these buildings, but the volumes of the buildings are totally different, even if the height is the same. And so it's not appropriate for that reason. So that is the end of that rant, but I think that's an important idea. All right, the next thing that I want to show is a little bit of R code. Here we go. So I'm doing this with the ANIST data set. I just arbitrarily chose to deal with FT feminists. That's the one we've been talking about as an outcome variable. And then FT socialists. FT stands for feelings thermometer. So how do you feel about feminists and how do you feel about socialists? And just because I wanted to get this done, here I've eliminated all the missing values. So this is the feelings thermometer values that are not missing. So I can make a scatter plot. Okay. And most of you discovered last week that this scatter plot is not so good. And the reason is the points are all on top of each other, right? So these are not really continuous variables. We're kind of pretending they are, but they're not really, right? They're bounded between 0 and 100, and they have to be integers. So this looks like a grid, right? How many people chose 50 for socialist and 50 for feminist? Well, I don't know, because all their dots are on top of each other. Is it more or less than the number of people who chose 0 for feminist and 100 for socialist? I have no idea, right? I can't tell with this plot. So I'm going to show you a couple ways to deal with this issue that all the points can be on top of each other. This can happen when you have a very large data set. It can also happen when you have variables that are not actually continuous, even if they're kind of continuous. And that's very common. So a few solutions here. One is to make the points transparent. You can do that in ggplot, but I'm doing it here without ggplot using a package called scales. And so if you look at the color argument here, instead of just saying color equals cornflower blue, I say color equals alpha, which means transparency. Tell it what color, and then this is a number between 0 and 1 that says how transparent it should be. Okay, let me omit this part for a second. Let's run this. Okay. So is it good yet? Not really, right? But you can see now that some of the points are lighter or darker than others. Okay. Now, the fact that these are empty circles, I think, is not helping. So that's what this piece of code was for, right? So let me run it like this, right? Is it good yet? No. Okay. But because the points are transparent, when there are a lot of them on top of each other, it appears a little darker. Okay. So this can often help. This strategy is especially helpful when you have, when the problem is that there are too many data points. So it looks like a big black dot in the whole screen, as opposed to the issue we have here, which is that the points are all literally on top of each other because we don't really have continuous variables. So let me do something else. The next thing I'm going to do is called a jitter. There's more than one way to do it. There's a function called jitter in R. You can also do it in ggplot, but I'm doing it here by literally adding some random noise to each of the variables that I'm going to use. So I'm setting a seed, so I want it to be the same if I do it again later. So this is the vector of all the socialist values, and this is a vector of random normal draws. The rnorm command takes 3 arguments. The first argument is, well, how many random normal draws you want. In this case, however many values there are in D, right? That's how many I want. So I've taken out some missing values. Right now, the number of rows in my data set is 3008. So this vector here is of length 3008. And I would like to draw 3008 random normals with mean 0 and standard deviation 1. And this 1 is something I can play with to make the random noise more or less. But I'm going to add random noise to both of these variables, because then it looks like this. And I kept the transparency in as well. And so now what I have is a blob, because the points are not on top of each other. There's a little bit of random noise on them. And now that I have blobs, I can say, hey, there's a lot more people who chose 50 for socialists and 50 for feminists, right? Then there are people who chose 100 for socialists and 0 for feminists, for example. I can see that among people who rated socialists 0, right, many more of them have lower ratings for feminists than higher ratings for feminists. And the opposite here, among people who had socialist equal to 100, many more of them have high ratings of feminists than not. Right now, the pattern is starting to show. Right, so this jitter idea can be extremely useful when the points are on top of each other. Again, what you're doing is you're turning each point into clouds of points. Do we now have some random noise in the data? Sure, but is it visible now? Yes, so it's worth it. Okay. Now, here's another solution that may not seem obvious. I'm going to make a box plot of the feminist values for each value of socialist. That might seem strange because we're pretending that socialist is a continuous variable, but it's not really, right? It's equal to numbers between 0 and 100, integers between 0 and 100, and also people tend to choose round numbers. So there's not actually infinitely many different possible values of socialists. So again, for each value of feminist, I'm going to make, or let me be careful. I'm going to make a box plot of the feminist variable for each value of socialists. This is feminist by socialists. Okay. All right. So now, again, for each value of socialist, I have a box plot. And look at this. Now I can see that there's a linear relationship between these, right? When socialist is 0, here's the value of feminist. When socialist is 100, here's the value of socialist, of feminist. One issue to warn you about here is that this axis here is no longer necessarily evenly spaced. Like if nobody chose 52 for socialist, then that's just skipped here. Okay, so that's just something to know. However, I would argue that actually this is better than any of the scatter plots that I was just showing you, because now I can see that there is a linear relationship. As socialist rating increases, the feminist rating clearly increases as well, right? We can see these medians and also the means then increasing in a very linear way. And it was not obvious the extent to which that was true when we made a scatter plot. Now, that's for plotting the data itself, but the same issues arise when you are making residual versus fitted value plots. So I'm just going to run a little regression of the feminist values on the socialist values, pretend I'm interested in that. And here is the residual plot. Okay, so you guys have made plots like this now on the assignment, on assignment 7. So this scatter plot has exactly the same problem as the scatter plot of the actual data, right? The points are right on top of each other. The points are right on top of each other. It's not easy to tell if the mean of the residuals for each fitted value is right at 0, okay? Some students have asked me why we have this kind of diagonal pattern. So here's the way to think about it. The fitted values are our predictions for a particular data point, right? The residuals are the difference between the actual response and the prediction. So if you chose, let's go up here and say this. This is people who chose a number close to 25 or so, right? The fitted value is about 25 for these people. Okay, so the prediction is 25. What's the highest value they could have actually responded? Well, 100. So the highest possible residual is 100 minus 25, which is 75. And the lowest possible residual, well, that would be if the people chose 0. And then the residual would be 0 minus 25, right? Which is negative 25. And we have it right there, right? And that's true for each of these different fitted values. Because the outcome is not actually normal, but rather it's bounded, right? We have to get this pattern. But it doesn't necessarily mean that the linearity assumption is terrible or that the equal variance assumption is not met. Rather, we need to deal with the fact that data points are on top of each other. I can't tell from this picture what the mean of the residuals is for this fitted value, or for this fitted value, or for this fitted value, or for this one. I can't tell whether the means actually decrease, right? Or maybe they are going to line at 0. So I'm going to try to use the same strategies that I was using for the original scatter plot to make this residual versus fitted value plot more useful for checking assumptions. So first, let me try making them transparent. Okay, does that help? Maybe a little. Then I'm going to make a jitter. And you know what? Why don't I also change the point types? These are filled in instead of empty. I think that'll help. Okay. All right. I would argue that this is getting better, right? When the fitted values are low, right, like around 25 or 30 or so, right, then usually the residuals are between negative 25 and 0, and more rarely are they higher, right? On the other hand, when we have fitted values that are quite high, right, usually the residuals are just above 0, but they're kind of spread out among there, right? But it's not the case, right, that the means totally follow this diagonal, right? Because you can see this is a skewed distribution. So its mean is maybe over here. This is a skewed distribution. Its mean is maybe over here. In fact, we can actually plot the means, right? It would be nice to plot the mean residual for each fitted value. And in fact, we know a way to do that. We know a way to do a connect the dot. That's called a spline. So I'm actually going to run a spline here. I guess I'll also put the horizontal line at 0 just to see it. I'm going to run a spline where I'm predicting the residuals using the fitted values, because what that's going to do is find the mean of the residual for each fitted value. So I'm going to run that, and I'm going to add those to my plot. And that red line is an approximation of the mean of the residuals for each fitted value right across these skewed distributions. And now we can see that this red line is right at the black line. So the linearity assumption here is true, right? For each fitted value, the mean of the residuals is very close to 0, right? Now the normality assumption is not true, because I can see that this is a skewed distribution and this is a skewed distribution going the other way. And all these distributions of residuals for each fitted value are bounded, right? I can see that. And normal distributions are not bounded. They can go from negative infinity to infinity, but at least the linearity assumption is clearly okay here, all right? Which is a long way from the first residual plot we looked at, which really doesn't tell me a lot about what I'm looking at. So going forward, as you work in the last assignment, I would love to see some residual plots that look a little bit more like this, right? Because you're still going to be dealing with the same data set. So this issue that the variables are not necessarily totally continuous is going to continue to exist. But this kind of plot can be extremely helpful. All right, I'm going to stop there. I'm excited to see what you guys come up with this week, and good luck as you proceed.